Hi everyone, my name is Sheldon Andrews, a professor at ETS in Montreal, and today I will be presenting about our work on distant collision response for rigid body simulations. This work was done in collaboration with my colleagues at McGill University, Coevoet, Denali Relles, and Paul Cry. So let's begin by considering a rigid body simulation involving impact. As we can see, the box in this scenario comes crashing down and collides with a table. Yet we are unable to discern important physical properties about the box. For instance, what is the mass of the box? Is it heavy or light? And standard methods for rigid body simulations leave a lot to be desired in terms of the secondary dynamics that are exhibited in this type of example. We therefore address this problem in our work. Specifically, we focus on modeling vibration response that arises due to an impact. Typically, if we'd like to simulate vibrations due to impact, a detailed elastic model is required. Assuming small deformations, a linear elastic model involving the mass, stiffness, and damping of an FEM mesh could be used to synthesize vibrations. However, to faithfully reproduce the high-frequency vibrations that occur in stiff objects, very small time steps are necessary. And even for linear elastic models, they are prohibitive for real-time applications such as video games and interactive VR training simulations, which we target in our work. And this is where our contribution lies. We approximate the vibration response to collisions in rigid body simulations by using a pre-computed reduced elastic model based on Modal FEM. To render this process more efficient, we compute the response using a digital IRR filter. The response is computed as a displacement at FEM nodes that is then rendered as an impulse at existing contacts, causing disturbances to objects already resting on the surface of DCR bodies. Our approach is efficient and is suitable for real-time applications, with update rates on the order of 100 frames per second achievable. And as you can see, it really livens up rigid body simulations. Our work is similar but complementary to work that has investigated enriching rigid body and kinematic simulations by storing auxiliary information in textures. Notably, bounce maps varied the coefficient of restitution across the surface of simulation bodies to produce more natural collision response based on the object geometry. Our work also draws on concepts presented in the dirt paper, which introduce modal vibrations that are excited by rigid body motion and digital IRR filter coefficients in textures assigned to the surface mesh. We similarly use a digital IRR filter to efficiently compute distant collision response. Galapo and colleagues also proposed elastic deformation textures to model a varying surface compliance for rigid bodies, whereas our work uses coefficients stored at nodal coordinates to compute a vibration response due to impact. Furthermore, we are inspired by work on modal simulations for synthesizing sounds. For instance, the work by Zhang and James proposed a method for modal sound simulations where all contacts are considered and boundary conditions are changed in order to produce high-quality contact sounds, albeit at a high computational cost. Conversely, our approach is fast to compute, and we simplify the problem by considering each contact independently. Other work in this genre has focused on generating sound for interactive simulations, such as fully automatic and the work by O'Brien and colleagues. Similar to our work, these approaches use a pre-computed modal model, but with the goal of rendering plausible sounds due to collisions. The first step in our method is to detect new collisions in the rigid body simulation that result in an impact. Then, these impact collisions are mapped to an FEM mesh that corresponds to the collision proxy used in the rigid body simulation. In our simulations, we use a collection of spheres, boxes, and convex meshes to render the rigid body simulation more efficient, but then compute corresponding points on the surface of an FEM mesh. We then compute an impulse response at distant contact points based on a force loading obtained from the rigid body constraint solver, which causes a disturbance at distant bodies. Let's look at each of these steps in closer detail. As a pre-process, we build an FEM model corresponding to distant collision objects in our rigid body simulations. By solving a generalized eigenvalue problem, we obtain a modal decomposition of the FEM mesh. However, only a subset of the modes are needed, and in our experiments, we found that using the first 20 modes is suitable. This gives a reduced modal basis matrix that we use to map displacements and forces to and from the reduced model. At runtime, the rigid body simulations typically do not use FEM geometry for collision detection, but rather proxy geometries such as spheres, boxes, capsules, and convex hulls are used. In order to compute a response using our elastic model, we therefore need to map impacting contact points from the rigid body simulation to the FEM mesh of our reduced model. We query a copy of the mesh containing only surface nodes, in other words, a triangle mesh, and this results in the barycentric weights that give the contact point in terms of the FEM nodal coordinates. With barycentric weights in hand, we transform the impacting collision impulse from the rigid body simulation to the reduced elastic model. The non-interpenetration impulse lambda that results from the collision is retrieved from the constraint solver and mapped to the reduced elastic model using a matrix of barycentric weights and the modal basis matrix. This gives a force, or rather an impulse, acting on the reduced model that we can use to compute a dynamic response in each mode due to the loading. Conveniently, this can be done independently for each of the resulting differential equations, since each mode is decoupled in the reduced model. I'll refer you to the paper for details on how to compute the coefficients shown in the ODEs here. We can determine the response of each differential equation independently by using a digital IRR filter to integrate the equations. We compute the filter coefficients in the same way as James and Pai in their work on dynamic response textures. Conveniently, even though the filter is evaluated over many steps, only the modal displacements Q of the previous two integration steps and the loading function R are required to compute a new displacement value. Additionally, the loading function is only required for the first step, and in subsequent steps we set it to 0. Alternatively, we could apply the loading function over a small number of time steps to simulate a smoother transition. The IR filter update rate is based on the Nyquist rate of the maximum frequency across all modes, which can be high for stiff objects. The filter time step, big T, is therefore several orders of magnitude smaller than the time step of the rigid body simulation, meaning that the digital IR filter rate is many times that of the rigid body simulation. However, evaluating the IRR is extremely efficient. Since the digital filter runs at a much higher frequency than the rigid body simulation, displacements computed by the IRR filter cannot directly be used to simulate a collision response. Rather, we compute the maximum displacement over all steps of the IRR integration, which we run for a single time step of the rigid body sim. This displacement corresponds to the peak amplitude of a wavefront due to impact. Then, velocity changes that result from the displacement are computed at existing contacts by linearly interpolating the velocity changes at nodal coordinates using the barycentric weights of the existing contact points. The velocity change is realized by applying an impulse at each existing contact. The impulse is computed by estimating the effective mass at each contact point, which involves the contact Jacobian and the mass matrix of the rigid body simulation. By taking into account the effective mass, the impulse is able to realize the desired velocity change at the next time step in the rigid body sim. For large objects, such as terrain, we observe that the vibrations propagate as a traveling elastic wave. If the source of vibration, such as an impacting collision, is located on the surface of the object, the vibrations will propagate and attenuate according to a decaying exponential. The amplitude at a remote contact is dependent on the initial amplitude at the source, the distance from the source, as well as several material properties. We therefore propose an alternative approach for computing the distant collision response for large-scale objects based on this model. We found that a simplified version of the attenuation equation produced plausible behavior, while also being more straightforward to tune. We compute a scaling of the amplitude due to material absorption by a constant parameter that is tuned for each specific scenario. Reasonable values of this parameter are discussed in the paper. We use beta equal to 0.5, 1, and 2 as the exponent term and observe that the response becomes more localized as the parameter is increased, which is expected given the role of this term to account for geometric attenuation of an elastic wave. Also, since we are mainly interested in the effect of traveling waves observed at distant locations on the surface, we use a geodesic distance between points within an elastic model to compute a response. In order to estimate the initial amplitude of the elastic wave, we sample the displacement at each surface node by applying a unit impulse. An offline FEM simulation with small time step is used for this purpose. Displacements are then retrieved by the rigid body simulation during an impact, and the amplitude is estimated by interpolating the displacement Q hat across FEM nodes and scaling it by the impulse from the constraint solver. Then, to compute the amplitude at a distant contact, the displacement is again scaled by a factor computed by the approximate attenuation model. Finally, we divide by the time step to compute a velocity change. Now that you know the technical details, let's see some results of distant collision response in action. Here, a heavy pot is dropped onto a table, causing plates and cups to jump. The collision response of the table is computed using a reduced elastic model. Observe that even stacked objects exhibit plausible secondary dynamics, even though they are not in direct contact with the table. Here we have the same scene, shown with and without the DCR technique activated. Using distant collision response, the scene is richer and more lively, with important dynamical cues about the impact being simulated. By comparing to an FEM simulation with small time steps, we see that distant collision response gives dynamical behavior that is qualitatively similar to the ground truth simulation. In this example, the cliff face is again modeled using an FEM mesh with pre-computed modal response. The impact of the truck hitting the base of the cliff causes the rocks perched above to come tumbling down. Here's an example using our spatial attenuation model. Observe that with an increasing value of beta, the area of effect of the computed disturbance is reduced. We also tested the spatial attenuation model using a large scaffold example. The C coefficient is tuned differently for the scenario, but the effect of beta is similar. The geodesic distance is computed and cast for each resting contact point, which is used in the spatial attenuation equation to estimate the distance from the source of impact. By optimizing for the parameters used in our spatial attenuation model using a data fitting technique, we observed that manually tuned values produce plausible results. For example, in the scaffold example, using values of C equal to 0.4 and beta equal to 2, the amplitudes are reasonably close to those measured in an offline FEM simulation. Finally, we demonstrate that our approach runs at interactive or real-time frame rates by reporting performance details for our implementation. The compute time using the reduced elastic model increases with the complexity of the FEM mesh and number of distant contacts. However, we observed that determining the barycentric weights tends to dominate the overhead, and we believe an optimized or parallelized implementation of this function could significantly reduce the compute time. Similarly, the spatial attenuation model was tested using the scaffold and lowrider truck examples, and compute times are comparable. However, in addition to the barycentric weights, the computation of geodesic distances introduces additional overhead related to the solution of the heat equation. Caching distance values of resting contacts helps, and we do this in a lazy fashion, which is why we report the first and subsequent impacts of the truck separately. To conclude, the true problem of computing vibrations due to collision is very messy. Simplifications are necessary to have a solution that can be computed in real time. We propose a simple collision model that gives a plausible response at distant contact points when impacts occur, and the approach is suitable for real-time applications. Furthermore, we have proposed a simplified model for large-scale objects with attenuation of traveling elastic waves. DCR provides important dynamical cues that are missing from many real-time simulations. We envision that our approach could be used in video games, virtual pre-production, and virtual reality training to improve the plausibility of secondary dynamics in these applications. However, the approach does have some limitations. Specifically, our approach ignores boundary conditions in order to simplify computation of the reduced elastic model. However, these could ultimately change the elastic modes. This is a large approximation, but we realize it in a physically plausible manner. Furthermore, there is no guarantee regarding energy conservation with our approach. However, we believe this would be an interesting consideration for future work. Finally, we graciously acknowledge NSERC and CM Labs for funding and supporting this research. Thanks for watching.